first of all, who is PROTOS? We are a company specialized on providing software tools, test tools, software architectures for embedded systems. So basically, we develop tools and methods, code generators, and so on. Who am I? I'm an aerospace engineer with a lot of experience in the field of embedded software architecture, testing, and tools. And today I'm going to give you a little impression of how we are going to test for robustness in embedded systems. So why are we doing what we're doing in the field of testing? Late testing is a real problem. The more complex it gets, the bigger the problem gets. And the later in the stage you are, the bigger the problem gets. So what we do is we bring the hardware software integration test and the system test to the desktop of the developer, because we need to learn and we need to test much earlier. So we're talking about minutes instead of weeks or months. That's what we do. And so now first question, if we're talking about robustness tests, is how do we derive test cases? Let's have a look at some principles for the derivation of test cases. It's only a small number of methods here. So we have certain methods to derive test cases for data, like equivalency classes, boundary analysis, CRUD matrix, and so on. And other methods for paths for different situations, like cause-effect graphs, and so on. And today I'm going to focus on state transition tests for path coverage within our software. And at the other end, in the data-related testing, equivalency classes and boundary analysis, and we can combine them to make really nasty tests to test for robustness. So the question, one question that always comes up is, how do we define coverage for this kind of tests? Of course, you can define a code coverage, the usual C0, C1, and so on, MCDC coverage, and so on. That's for robustness tests. Might be useful on a lower level, but on a higher level, software integration, hardware software integration, system testing, that's usually not a good metric, because it's too fine-grained. So what we're talking about here in terms of coverage is state transition coverage. So state transition coverage not for the target you're testing, for the system under test, but for the test cases you're creating. So situation coverage, if you want. And the metrics here are N-switch and transition coverage. And for data coverage, for example, we can use pairwise, n-wise coverage, combinatorial data coverage metrics, and so on. So that's on a higher level, and that's usually those are very good metrics for robustness tests. So now let's talk about state transition testing. That's the method we're using for robustness testing, for very deep testing of many situations. So the basic idea is you define a state transition graph, not in your system under test, but in your test system. So that's the black box description of all the paths through your system. So all the externally stimulated paths through your system. So a state transition test is a black box test usually. The state transition diagram is a formal contract that defines the expected external behavior of the system or a component. So it can be done on any level. And every transition is a test step. So that's important, because we want to generate the combinatorics, but also we want to test them. And every path from initial to end is a test case. The goal is to at least make a complete state and transition coverage. This would be zero switch metric. So every state and every transition covered at least once. Better is a path coverage with higher level N switch, so combinatorial path coverage or combinatorial data coverage. And for higher metrics that automatic generation is very useful. You can do this method on a piece of paper. I'm going to show you that, but for real robustness test, code generator would be nice. The idea is here now, from initial to end, every path is a test case. So you can see we need a couple of test runs or test cases to cover all the paths here. So in this case, maybe 5, 6 test cases. That's a very simple graph, of course, for a traffic light, for a pedestrian crossing. Now let's start with a piece of paper. We create a state transition test on a piece of paper. So for example, we have a system with a motor. We can turn the motor on, we can turn it off, we can change the speed, we can brake it, we can change the mode from mode 1 to mode 2, maybe using a different setup or something like that, different hardware, maybe different configuration. And now we want to cover all the paths through our system as test cases. So first of all, we derive test cases. So test case 1 would be from initial to end, taking this path, the blue path here. And they see, as you can see, we have not covered those 2 states with their transitions. So when the motor is on, we also want to test the brake. So now it tests the brake. That's the second test case. So now we have covered all the paths for all the transitions and all the states. But now I have not tested, for example, braking in mode 2 or change speed in mode, braking in mode 1 or change speed in mode 2. So that's why I need the higher level metrics. So for example, I would need the green path here to cover change speed together with mode 2 and brake together with mode 1. So in this case, this would be end switch 1, for example. And I also want to cover loops, because I do not want to stop at the end, but I want to run this more often with different combinations and so on and so on. And in that case, you get many more test cases. It doesn't really explode combinatorially, but you get much more test cases. So those would be some more test cases if you make higher level metrics here. So now let's have a look at state transition tests with a generator. We design with our method, we design the test case model from initial to end, as you've seen before. So for example, in this case, the UR is active for the motor, and we set different parameters to the motor, and then we run all the tests here, also loops. And by that, creating many different possible paths through my system. As said before, that's a black box description of the expected behavior. That's not the state machine in your system. If you want to test a single state machine in your system, you can do this as well. Then the test case would be similar, would look similar to the system under test, but on a integration level or on a higher level test, system test, and so on, that's usually a very, very different state transition test. And that's important because it needs to be redundant to be useful as a test case. So now that's how you design your test universe, if you will. And that's what the code generator does. It generates the documentation, as you can see here, but it also generates the executable test cases. In this case, for end switch 1, for a little combinatorial test cases, we have 15 different test cases to cover all the combinations here. And so the state transition test is a black box, describes the black box behavior of a system, and the test generation generates the test cases to cover all the path and data combinations to cover your system as good as possible. Now, let's have a look at the end switch metric for path coverage. So the goal is a state transition test for the state transition coverage. And we want to complete path coverage up to a certain level. So 0 switch, every transition at least covered once. one switch all the combinations of 2 transitions at least at once, and switch all combinations of n+1 transitions all at least once. So that's again, that's 0 switch, and that's 1 switch. So we with 0 switch, we would not get the green and the red path here. With 1 switch, you get the green and the red path. With 2 switch, you get more. So that's the idea of the path coverage in the state transition testing. And we can also use the same method to cover n-wise for data coverage, so pairwise, n-wise. So the goal is to cover all the data combinations. We start with equivalency classes and boundary analysis for each parameter, test as test vectors, pairwise, two-wise, all test vector combinations for 2 parameters, and n-wise all combinations for n parameters. As an example here, if you have parameter A with 3 different values and parameter B, you would need 9 test cases to cover all those combinations here. So how we do this with state transition test? For the n-wise coverage, we define the parameters as a single test step here. So for example, we set the parameter A here to those 3, to one of those 3 values, and parameter B here. And so that's the definition for parameter A, that's the definition for parameter B. And as I said, every pass through the system here, through the state transition graph, is a test case. So for example, for the test case 10.7, we generate this path here. So actually we need to generate 9 different paths for just for the data combination. And of course, more different paths for the tests down here. And now we combine the path setting of the different parameters. You do not have to do this at the beginning of the test. You can do this at any point in the test. You can combine data and path coverage at any point here. But to keep it simple, we set, for example, different parameters, different setups for your software, for example, and then we run the n-switch coverage. So data coverage, path coverage, and with higher metrics, you get the complete data and path coverage up to a certain level. That's very good for robustness tests here. So why all the effort? We find sporadic errors that are hard to detect and debug. If you know the situation, you have hundreds of applications out there, hundreds of customers, and at one customer you have 1 error a year, and that's really hard to detect. So that's something you can find really good with robustness tests. So we find race conditions. That's most likely, if you have such a sporadic error, that's a race condition that only occurs in certain conditions, so certain timings, in certain situations with certain parameters. So that's why they are so hard to find. You find side effects because you try it out, you give it a try, you try all the combinations. You also can run stress tests to see whether your application runs stable for a longer time. You stress test always with the same test setup. If you loop it, that's not a real stress test. A real stress test is you have very different situations all the time, and that's hard to do manually. You can also run performance tests to see in those different situations how your performance behaves. Because only running the same test over and over again for performance tests might not give you a good picture of your real performance. And you can run long-running robustness tests. That's the goal here. It's also very useful, of course, for safety or security relevant systems. Now, how do we do this from a hardware perspective? We have a little mini-hill application here. So that's the blue one. We put the system under test, in this case, STM32 chip with the complete software as it's delivered to the customer. We put this on this board here. Then we connect all the pins of the microcontroller over this patch panel with our test system. And on the test system, we need to do three things. We need to bring the signals, so all the digital analog signals, all the low-level bus systems, PWMs, and so on. We need to bring them into our test system. Then we need environment simulations because, for example, if you do not attach a motor or a battery that is controlled, your system fails immediately. So you do not even get to the point where you actually can test different paths in different situations because your system fails. So you need to simulate the environment. That's a very important part. And once you've simulated the environment, you can run a lot of different test cases because you're basically running your test cases against a simulation of your environment. So that's the basic idea. And we have a model-driven development toolkit to model the environment simulation and the test cases. So always the structure and the behavior of simulation and test models. From there, we generate the code. Also, of course, the state transition tests, the combinatorial tests. We compile this, we flash this to the test system. We need to run it on the test system because it needs to be hard real time. So Python script on your laptop does not work with 20, 30, 40, 50 kilohertz, but a motor simulation or a test for a motor simulation needs to run very, very fast. Sometimes even in the megahertz range. So that's very important, and that's why we use this very specialized hardware and software setup here. And then we log while we're running the test cases, we log the test cases, we convert it into diagrams to be able to analyze what happened afterwards. So for example, you need to know exactly what happened, why your system failed. And that's very good to have a diagram to show you what happens there. So then we learn and iterate. We also use continuous integration with staging for robustness tests. So because what I want is I want a fast running test in a commit stage. In this case, you see 8 different mini-hill setups for 8 different targets, 8 different projects, whatever it is, maybe for a product line, something like that. But you want, after every commit, within a couple of minutes, you want to know whether your system works again against all the tests. But the longer running tests, the robustness tests, they need much more time. I still want this fast response. So usually we test every code change for every developer within minutes in the commit stage. Also your requirement tests, your every test case once, every error situation once maybe. But the longer running robustness tests, they might take an hour or maybe overnight or over the weekend. So we run them in a second stage, in the capability stage, with the performance tests, with the robustness tests, with the safety tests, and so on, because they need longer. So we still have this fast response in the commit stage, but for every other hour, for example, you run the robustness tests. So that's also very important. So now let's have a look at my little demo I brought you. We have a system under test with a BLDC motor control system. It generates 3 PWMs. We have in the test system a motor simulation that returns 3 Hall signals, could also be analog signals or whatever it is your motor uses to be controlled, temperature sensor, UART, and so on. I don't want to go too much into detail. On an electrical level, the test cases look like this. Here you can see the PWMs, the Hall signals. We change the speed, we trigger errors, you see the PWM shuts off, and so on. And we do this in a lot of combinations. Here, for example, you see the equivalency classes and the boundary values for the temperature. That's an analog value where we simulate the temperature. So now, that said, I'm going to jump into my demo. Let's have a look at the development environment, just a brief introduction there. So here you see the development environment, model-based with the IO layer here, that's the simulation layer. Here we have a motor simulation that really behaves as a closed loop motor simulation. and here we have the test cases. So now let's assume we've done our work here right. So we created an environment where our system actually can run. Now I need to create test cases. So now let's have a look at the test cases. On a lower level, we create test steps, for example, to set the speed, to check whether the speed in the motor simulator is the one expected in my system under test or vice versa. So those are the little test steps I need now to recombine two bigger test cases. So I can run bigger tests. For example, I can combine the steps into sequences and in the end into test suites. So that's here you see the specification for this test case that's generated automatically. So now I have my test steps, I have my test cases, and now I want to combine them into higher level tests. So now let's have a look first at a little demo, state transition demo test case. So here we have a little demo. We use a textual language to describe the state transition test graph here. For every transition, we can trigger a test step, we can trigger a sequence or whatever it is to make sure that this step actually works. So now it's just a demo to show the combinatorics. And now if I generate the diagram here, let's have a look at the generated diagrams, and of course also the test cases are generated. So for n switch 0 with such a simple graph, you only get one test case. That's not so interesting. Now let's make our test a little bit more complex. So let's say we want to go different paths, for example, from state between the different states. We want to go different paths here. So path 1, path 2, path 1, path 2. Now I'm generating the not only the documentation, but also the executable test cases, but I'm only showing you the generated documentation. So here you see, now that's the graph again, and those are 3 test cases because we said we want to cover all the states and all the transitions. But as you can see, we do not cover, for example, here path 2 against path 2. Here I have path 1 against path 1, 2 and 1, but not path 2 against path 1 and 2. So with n switch 0, I get this. It's completely correct. So, but I want better coverage, so I tune the n switch metric a little up, and I generate the test cases new. And suddenly you can see we have 4 test cases, path 2 against path 2. Now let's make a jump back. Let's build in a cycle here. So let's go from, for example, from state 3. Let's go back to state 1. Just to have a cycle here. And now I'm tuning the metric a little bit to n switch 3. Let's generate the diagram and the test case again. And yeah, here you can see that's the diagram, the black box behavior I described, and those are the needed test cases to cover all the combinatorial paths through my system. And the path now can be really a message or a function call or something like that, but it could also be a different parameter definition. And by that, we can combine parameter combinatorics with execution combinatorics, with path combinatorics. So that's the basic idea. Now I'm going to show you the state transition test just briefly for the motor control system mentioned before. Here, for example, I test the required speed with 10%, 50 and 90%. If I would do the boundary analysis, I need to add here, for example, 1 and 99% of the speed, something like that. So that's how it works. And of course, now many more paths are generated for the test here. So let's go back, and now let's run the let's run the test cases. I'm going to, you can compile and flash here. I can also do this with this little graphical user interface. Now I'm going to show you my test system on my desktop. That's the one. And I'm going to run the state transition tests and all the other test cases as well. So I'm connecting with my target, and now to show you a little error, let's assume we have in the system under test, we have an error, a bug. I'm pulling this cable to introduce a little bug here. Of course, that's normal, not what I do, but so now the test cases are running. They're testing, checking everything, and I see the problem here. Those are the state transition tests, so the robustness tests here. And when I click on the first problem here, you can see in the IDE where the problem occurred. This occurred exactly here, activate motor control. That's exactly the step we're talking about here, or where the problem was. So now I repair this, I run this again. And usually I only run, maybe if it takes longer time, I only run the tests that failed. And then in the end, I run everything, and now I see everything is green again. So we can also do this with continuous integration, of course. So for example, if I change anything, I can run the Jenkins server with continuous integration. So I'm going to really to break the system. I'm jumping into the code. That's now the code for the system under test. So far we've developed the test system. Now we're jumping into the code of the system under test. Let's assume I'm a developer, application developer now, and I just want to run the test cases on the continuous integration server on every commit. I'm going to revert this here. And now I'm going to, I'm going to into the motor control of my system, and I'm introducing a bug. Let's set the duty cycle for the motor, for the PWMs, to 20%. So now the motor would run constantly with 20% duty cycle. And of course, something needs, we need to detect this now. Now I'm going to commit this. Let's call this bug. I'm going to commit this, and when I commit this, I will jump immediately to the continuous integration setup. Here you see the continuous integration setup. And here you see it already triggered the continuous integration server. Now let's have a look what happens. The continuous integration server checked out the new version of the software, of the system under test. It assembles the project, in this case, the system under test, not the test system. Now it flashes the test system. Here you see, it just flashed the test system. Now it's going to flash the system under test. And now it runs the tests. We can also have a look at now it failed. Why did it fail? Because I'm still connected with my graphical user interface here. So let's trigger this again. Sorry, my bad. I'm going to trigger this again. So now it's checking out again, assembling, flashing. And yes, you can see it runs really fast. So now it flashed. System under test, test system. Now it runs the test. You can see the logs. That's the command line log. It's the old log from before. Some projects still using this, so we still maintain this. But the really interesting things are the reports now, because now I see my test cases are yellow. So red is it could not build. Green, or white in this case, is everything's okay. Also the test cases. Yellow means it could be built, but the test cases failed. Now I can click on the last test results. It's the motor demo integration test. So I know exactly which test case failed, but the more interesting detail is why it failed. So let's click at the diagram. And that's again the same diagram I've shown you before, but now on the continuous integration server. So this expect failed here. I'm clicking on this, and jumps back into the development environment and shows me exactly where the test case failed. And now it's up to you to find the problem. It helps a lot to have this equipment on your desktop, because you can just attach a debugger, and while the test case is running, debugging, monitoring, putting in breakpoints, look at parameters or whatever you need, because you can reproduce it. That's the important thing here. You can reproduce the problem, and once you've repaired it, you commit it, and the continuous integration server tells you everything is okay. And you do not want to wait for an hour or maybe a night or even a weekend at your desktop for the equipment to run. That's something the continuous integration server can do really, really good. Okay, so that's so far the demo. Let's jump to the conclusion. So we want to make your software more robust. You can reduce the effort to develop many test cases with this method. You can do very, very deep testing for variants and product lines. So state transition tests are a very good method to define test cases for path and data coverage. And also state transition tests can be used without tools, but for combinatorial test cases, modeling tools are really useful. Because imagine those hundreds of or even thousands of test cases, you don't write them manually. You can generate them. That's the way to go. Okay, so that's it from my side. Thanks for your attention. If you have any questions, don't hesitate to contact Hitex or me at PROTOS directly if you want, and we will answer your questions or discuss your testing problems or requirements with you. So thanks for your attention.